I'm Pat Dugas. This screencast is about taking radical expressions and being able to add, subtract, multiply, and divide them with the goal of simplifying them. So let's look at a couple of properties that are going to help us with that. First of all, the product property of radicals. Now, it's very critical that in both these properties, you're going to see the product and the quotient properties. The index must be the same. For any numbers A and B, real numbers, and any integer of index greater than 1, the nth root of the term A times B is equal to the nth root of A times the nth root of B. And it works both ways because it's an equation. So for example, the square root of 2 times the square root of 8 is equal to the square root of 16, or 4. Also, the cube root of 3 times the cube root of 9 is equal to the cube root of 3 times 9, or 27, which also is 3. There is a quotient property for radicals as well. As long as we have real numbers A and B, with B not being equal to 0, of course, and for division by 0, and any integer of index greater than 1, same rules as before. The nth root of A divided by B is equal to the nth root of A over the nth root of B. So the square root of 27 over the square root of 3 can be simplified down into the square root of 9, which is 3. In terms of cube roots or other nth roots, the cube root or third root of x to the 6 divided by 8 is the same as the third root of x to the 6 over the third root of 8, which is the same as x squared, because the third root of x to the 6 is x to the second. And the third root of 8 is 2, or another way to write that is 1/2 x squared. So those two properties, super helpful. In all these properties, though, we got to have the same root, the same index. Also, you're going to see the term simplifying. What does it mean to simplify a radical expression? Well, the index, the root, needs to be as small as possible. Ideally, you would get rid of it completely. The radicand, that is what's inside the radical, can contain no factors other than 1 that are nth powers of the integer, because if they were, you would take them out of the radical. And the radicand should contain no fractions as well, and certainly no radicals appear in the denominator, and we're going to rationalize the denominator to get rid of any radicals in the denominator. So let's look at the product property example of simplifying expressions. So if I have the cube root of 125m to the 30th p to the 20th, I'm looking at things to the third power to break them out of this radicand. So 125 can be written as 5 to the third power. M to the 30th can be written as m to the 10th to the third power. And p to the 20th, well, that's a tough one, okay? So what we're going to try to do with p to the 20th is look at groups of 3. And so 20 divided by 3 is 6 with a remainder of 2. So if I take p to the 20th, that's like p to the 6 raised to the third power. That takes care of 18 of our p's multiplied by each other. And that leaves us with 2 left over. So you can see we're trying to get rid of as many groups of 3 as possible. So when I take that down, that can be broke up in the product property as the cube root of 5 to the third times the cube root of m to the 10th to the third times the cube root of p to the 6th to the third times the cube root of p squared. This is kind of the remainder. So cube root of 5 to the third is just 5. The cube root of m to the 10th to the third is just m to the 10th. The cube root of p to the 6th to the third is p to the 6th. And then we're left over with this last term, the cube root of p squared. And that is in simplest form. Let's look at the quotient property and how it works. So if we take something like the square root, remember square is kind of like this, it is the second root, of y to the 8th over x to the 7th. That's the same thing as the square root of y to the 8th over the square root of x to the 7th. And so I'm looking for powers of 2 to break that up. 8 divides by into 2 4 times. So this is the same as the square root of the numerator is the same as the square root of y to the 4th, all raised to the second power. If I take x to the 7th and take the second root of it, then I've got x to the 3rd raised to the second power with 1 x left over. So this is like x to the 6th times x to the 1st. So notice I'm trying to get in groups of second power terms. So what happens is the radical 2, or root 2, and the squares, inverse operations cancel each other out, and I'm left with, in the numerator, y to the 4th, and in the denominator, x to the 3rd times the square root of x. And that's not all I can do with it, because one more step is to rationalize the denominator, because we can't have radicals in the denominator. if it's in simplest form. So I'm going to multiply the square root of x. Now, why do I multiply by the square root of x over the square root of x? Well, I'm multiplying by that to get rid of the square root of x in the denominator. And since this is algebra and I can't change the expression, I'm multiplying it by 1, the square root of x over itself. So when I do that, I get y to the 4th times the square root of x in the numerator. And I get x to the 3rd times the square root of x times the square root of x, which just becomes x, because the square root of anything times the square root of itself becomes that thing. And so I get x to the 3rd times x in the denominator, which is actually x to the 4th. And this is in simplest form. Let's look at an example where we're multiplying radicals. Okay, so if I'm asked to simplify this, 5 times the cube root of 100a squared times the cube root of 10a. First of all, I got to make sure these indices are the same. They're roots. They are. So they're kind of like terms because they're using the same root. So this becomes 5 times the cube root of 100a squared times 10a. We're actually using the product property of radicals in reverse. Sometimes that's helpful for us because I'm looking at this and I don't see anything that's in nice groups of 3, but if I multiply them, I might be able to get that. In fact, I do. This becomes 5 times 1,000, which is 10 to the 3rd, times a to the 3rd. So by combining them, I get some nice cubes that will cancel out by cube root. So inverse operations are going to happen, and I've rewritten them in terms of the product property of radicals. And inverse operations on the cube root and the cubes are going to cancel out those. And so I get 5 times 10 times a, or 50a. So all of this simplifies down to 50a. Let's look at an example where we're adding and subtracting radicals. Now the key here is I've got to have like terms. These properties only work when we're using the same root. So here I've got 3 times the square root of 45 minus 5 times the square root of 80 plus 4 times the square root of 20. Okay, these are all second square roots. So I'm going to be able to operate on them further. Okay, so I'm looking, since it's square roots, I'm looking for perfect squares. Well, 45 is the same as 9, which is 3 squared times 5. So this first term can be rewritten as 3 times the square root of 3 squared times 5. 80, well, got to think about it a little bit, but 80 is 16 times 5. 16 is a perfect square. So this becomes 5 times the square root of 4 squared, which is 16 times 5. And finally, I've got 20, which is 4 times 5. So I can rewrite this term as 4 times the square root of 4, which is 2 squared, times 5. So notice, again, I'm trying to get as many squares in there so that the square roots will cancel those out through inverse operations. So using the product property, rewriting this, I get 3 times the square root of 3 squared times the square root of 5 minus 5 times the square root of 4 squared times the square root of 5 plus 4 times the square root of 2 squared times the square root of 5. These are going to simplify down. The 2 in the index and the 2 in the power will cancel each other out. Same thing true here on this term, and the same thing over here on this last term. Everything else is going to stay the same. We'll see what happens with it. So we get 3 times 3, because the square root of 3 squared is 3, times the square root of 5 minus 5 times 4 times the square root of 5 plus 4 times 2 times the square root of 5. We can take that a step further. And so this becomes 9 square roots of 5. All of this moves down to this term. This becomes minus 20 square roots of 5. And this becomes 8 square roots of 5. Now, since I have the same root and the same number in the radicand, I can actually add and subtract these terms as if they were like terms, because they are. Because they all contain that square root of 5 piece. So 9 square roots of 5 minus 20 square roots of 5 is negative 11 square roots of 5, plus 8 more square roots of 5 gives us negative 3 square roots of 5. And that's our answer. So let's look at another example of multiplying radicals where we're actually going to do some distribution. We're going to use the distributive property. So we get 2 square roots of 3 plus 3 square roots of 5, all times 3 minus the square root of 3. So I'm going to go ahead and distribute the 2 square roots of 3 and then the 3 square roots of 5 to both terms. So when I do that, I get 2 square roots of 3 times 3 minus 2 square roots of 3 times the square root of 3 plus 3 square roots of 5 times 3 minus 3 square roots of 5 times the square root of 3. So this can be simplified down to 6 square roots of 3. This here, the square root of 3 times itself is 3. So we get 2 times the square root of 3 squared. Then we have 9 square roots of 5 minus, and using the product property in reverse, 3 times the square root of 15, because the square root of 5 times the square root of 3 is the square root of 15. Okay, so we're moving through this process of simplification. Okay, so 6 square roots of 3, there's nothing more we can do with that. Negative 2 times the square root of 3 squared is negative 2 times 3, negative 6. 9 square roots of 5. When we have a prime number inside that radicand and we're just taking a square root, we can't do anything with it. And then we have minus 3 square roots of 15. This is now in simplest form. This screencast has been about operations of addition, subtraction, multiplication, and division with the intent of simplifying radical expressions.